The questions I would like us to answer today, or I will describe them to you today, is exactly what Juliet wondered about Romeo. So why do the knowledge graph exist? What good do they do us? How can we use them, and why do we love them, or why do I love them, I should say. So the story is, of course, old. So once upon a time, there was a thing called a connection. And this is something, it's a very simple notion, but it's fundamental about how we interpret what knowledge is and how we use it and how we form it. So this is also the basis for knowledge graphs, because knowledge graphs are basically just a whole bunch of connections. And what they do is they actually help us, among other things, they help us structure the information that we get, right? So if we think about the text, and there are all sorts of facts spread out in this text collection, the knowledge graph is sort of the next step that sort of connects all these different pieces and gives us a different and richer view about what the information that we have in this data is. And of course, one of the things that I will talk about today is how we go from this first level of sort of obvious connections to find deeper information, patterns, and meaning in these knowledge graphs. So people have realized that the way to provide a machine with knowledge, the sort of basic way to do that, is to try to represent things the way we understand them in terms of connections, gather a lot of it, as much of it as possible. At the beginning they thought we actually could formalize all of it and give it to the machine, so they in turn can reason and use this information to perform higher level tasks. So you probably know that all these endeavors have started a long time ago. So they started in the 80s when people started these two projects, Psych, which was focused on gathering encyclopedic knowledge. It was curated by knowledge specialists, and they have worked on it until these days, and still the information they have is not complete enough. And WordNet, of course, which I know you use and love, or used to love, who contains lexical information in terms of this relational model of meanings, where we have word senses that are defined in terms of their relations to other word senses. And after that, of course, we moved one step further and we got Wikipedia that sort of spawned out these various resources. One of them is Freebase, which, if you remember, started with info boxes in the Wikipedia articles. They contain nuggets of information about the entities described in those pages, and they proved very useful and very desirable for a variety of applications. So people have then, so they were extracted and people built on top of that in a collaborative way. And that endeavor is also finished. So contributions are close to that, but the data is still available to us, and we use it in various subsets of that for various applications, and I will do the same today. And then, of course, the revolution came when people realized that we can actually mine for the knowledge we want in text and sort of build automatically or semi-automatically these resources that we so much want. And there are, of course, various approaches to that, and I will say a few words about NEL a little bit later. And of course, the one that encompasses them all, right, so the ring to unite them all, is linked open data, that basically wants to combine all these knowledge graphs, knowledge bases, or knowledge repository, more informally called, and provide them in one unified environment, like one big meta-knowledge graph. Which brings with itself a variety of problems that we are not going to talk about today. So throughout this talk, I will mention two main knowledge graphs. One of them is Freebase, that I just mentioned before. So like I said, people have been using this because it's so convenient, it's so big, it provides enough training data, enough development and test data, so we can use it. And people have been using various subsets of this one for a variety of experiments, and as I will do also today. And the other one is NEL. You are probably familiar with NEL. So NEL is an acronym for Never Ending Language Learning. It started at the machine learning department at the Carnegie Mellon, and it started from this assumption or hypothesis, I should say, that when you learn things together, it's easier than when you learn them separately, right? So instead of learning instances of like some sports team is located in a city, then it's better if we learn together that the players of this team are located in the city, they had games there, their base is the stadium that is located in the city, because basically all of this information sort of disambiguates each other, and you sort of bootstrap a lot more knowledge in one step. So Nell started with a knowledge graph consisting of categories and some instances for these categories and relations between them, and has been continuously growing since, I forgot, I think it's something like 2008 or so. It has some minimal manual intervention to check whether the automatically gathered facts are correct, and then some of feedback is given back to the process to update itself. So what are knowledge graphs actually good for? Why do we want them? Why do we want to use them for? And I hope you are also convinced that they provide a large amount of structured data for machine consumption, right? So one of the things that machines need is something very well formalized, and knowledge graphs are particularly appropriate for that because they have nodes which are disambiguated most of the time. One node contains a variety of information about its relations with other nodes, and so on and so forth. It's also they are also easy for us to understand in this symbolic incarnation, because you can just look at them and you see, oh yeah, so University Babeș-Bolyai is located in Cluj-Napoca, it has this many students, it has these departments, so it's a very nice way to represent data in a way that's easy to understand at the first glance. When you build a knowledge graph from some unstructured data, I think it has this very strong advantage that it provides for you a new perspective on the data. So I show you just a snapshot in a second about a graph that some students of mine built in the knowledge graph course. So basically they took a collection of very old German documents that span like 700 years. It's called Regesta Imperii, and these are all sort of decrees that an emperor or a pope did. So he conferred some title to somebody, he conferred land to some churches, and so on and so forth. So once you manage to summarize this data in a graph format, you immediately see which emperor had the most interactions, what kind of entities they had interactions for. It's mostly people, church, and other entities, other types of entities in those historical times. Another very important aspect of knowledge graphs, and I will talk about that a little bit more today, is the fact that the structure itself allows you to enrich it, right? So I'm sure you have learned about link prediction efforts using knowledge graphs. So basically, you find some representation of the nodes and the edges and the relations, and then you use this representation to predict edges in this graph that don't yet exist. So this is, I find it especially interesting and sort of miraculous. And of course, one of my favorite applications for knowledge graphs would be discovering new knowledge. So I'm sure that you have a lot of papers to read. There are lots of new papers coming up all the time, and sort of I stress sometimes that am I missing something? If I read something else, would it sort of, all the pieces of the puzzle would fall into place, and I will have this epiphany about some very deep ideas of NLP and machine learning. And I think it's a good question, because I'm very sure we are missing something. So people work in adjacent domains, but now you have to go very deep in your own domain, and then you're probably missing things at the border where the intersections are, and discovering those would be extremely beneficial. So this is not just, a new idea and stuff. This is actually something quite old. And does anybody here suffer from migraines? No? Okay, so you do?
From time to time.
Well, not all the time. Hopefully not now. Hopefully I won't give you one. But so if you go to the doctor, did they recommend magnesium?
Yes.
So that is something that a non-doctor has discovered. So maybe you have heard about Swanson linking. So Don Swanson, he was working in library science, if I'm not mistaken, and he had this idea that you have all this research in complementary domains, and people don't know the intersection between these. So he made some investigations, and starting from migraines and extracting manually, so this was work manually done in the 80s, the connections between migraines and various causes, and what exactly chemically happens in your brains during migraines or to cause a migraine. And he then moved to the complementary domain of biochemistry, and he realizes that magnesium has some influence in the synapses and the connection between certain ions that facilitate the synapses, and they have an influence on migraine. So basically, by looking where these two domains intersect, he proposed a hypothesis, because he couldn't check it, that a supplement of magnesium would be helpful for migraine. So he proposed this to doctor, and actually they confirmed it, so that's why doctor suggests we take some magnesium. Sometimes it works, sometimes it doesn't. And he had some other discoveries, but sort of maybe the reason why you haven't heard a lot about these things, although there have been automatic efforts to make this process automatic, is that it's very, very hard, first of all, to find the significant points where two domains interact. And just extracting the right nodes and edges, it's still a work in progress. But I think we can move in that direction, and I love this application. I hope we'll get there soon. So, knowledge graphs, they're already out there. This is one that Google built, and you can navigate it to see, you know, various, this I think it's based on Wikipedia. You see connections between people, their works, and so on and so forth. And this, like I promised, is a fragment of a graph. So this is a temporal fragment of a graph that my students built from the Regesta Imperi. And you see the center point are emperors, and then all the historical entities they had dealings with, and what they did, and it's a fun graph to explore. So what are these knowledge graphs that I already talked so much about? Well, it's a heterogeneous information network. It's heterogeneous in the sense that you can have different types of nodes, so they don't all have to be the same kind of nodes. They have different types of edges, like different relation types, and but they are very nicely structured, right? So usually we interpret an edge representing like a subject-predicate-object triple, usually if they were collected from text, or we can think about it as just argument relation and argument. So while I'm going to talk mostly about the vanilla version of the knowledge graph, so it's like a normal graph with binary edges, there are all sorts of enhancement on that, and we can have hypergraph and all sorts of variations that can make this representation quite plastic and capturing a lot of good information. So one of the questions that we had before, like why use knowledge graphs? Of course, there are good parts and bad parts, and the good ones I already told you. I think they are a very convenient and flexible representation structure, and we have seen particular, so in my work I have seen that this idea that it provides a structured view of a very large collection of data, this is really useful, particularly in the digital humanities where people are very used to making sort of micro-analysis. So they take an aspect and they analyze one thing, following it through papers or digging very deep in one area. But what they don't do, because they cannot do, is doing this kind of macro level analysis where you have something that assembles a huge amount of data that obviously you couldn't work on it manually. And all this high-level view, I think, is very useful, and I'm going to talk about it, and I think this is one step towards this discovering new knowledge, is finding interesting patterns and regularities that can be exploited later on. And of course, they can be integrated in natural language processing, and they can be integrated in at least two different ways. And I love this thing about them, because whereas they started as symbolic structure, right? So you have the nodes that have a meaning, and then you have the edges that have also a meaning, and you see them there. For the past almost 10 years now, there were efforts to embed them in continuous vector spaces, right? So now we have also this continuous representation of graphs. You have maybe usually vector representation of the nodes. The edges can be vectors, can be matrices, and you can work with them in deep learning frameworks. So what is the bad part? Well, the bad part is that whatever we do, and sort of these very long-lasting manual endeavors have shown us, they are doomed to be forever incomplete. And maybe the bad part is not necessarily that they are incomplete, but they are incomplete in an imbalanced way, right? So what I mean by this is that you have, and these are some, this is Freebase. These are plots for Freebase. This is WordNet, and this basically plots the frequency of first argument, second argument, and relation for. So this was for data that had a train, dev, and test split. But it's enough if you look at the training data, which is in black. So this is a logarithmic scale here, and you see for Freebase you have quite a few. Instances that appear as arguments less than 10 times. And in these, in the work that relies on embedding graphs in continuous vector spaces, it relies on frequencies, right? Just like SVD and stuff like that. In order to build a good representation, you need to have that node or that relation appear frequently. Otherwise, the representation you get back will not be informative. It's like low frequency words in a corpus, right? So the more frequent a word is, or in between certain levels of frequency, because if it's too frequent, then we get into other troubles. But if it's below a certain frequency, the representation you are going to induce is not going to be representative. And since everything else after that relies on these representations that you build, then this imbalance is actually hurtful. So this is actually the main part of my topic today, and I'm going to look at it from 3 different points of view, is how to correct this incompleteness while compensating for the inevitable imbalance. It says, is there something ugly about graphs? I actually find them quite beautiful, so I just put a picture there for you. So since the main idea was that you can build a graph starting from, so we do away with the manual interventions, but you can use existing text, or like I just said before, you can bootstrap yourself new edges from the information that you already have. So we can have this schematic view about how to grow and complete knowledge graphs. In the interaction with the text, you have these 2 models. One of them is the push model and the pull model. So push means you process your data, you collect a lot of relation instances, and then you push them into an existing knowledge graph, or you make a new one based on this information you have. The pull model is when you selectively extract something from the text. So let's say I know about University Babeș-Bolyai, it's in Cluj-Napoca, but I don't know where Cluj is, right? So I would like to analyze some resource, maybe Wikipedia, and find information about where Cluj is. So when I'm targeting some specific information that I want to pull into my graph, that's the pull model. So the other one, this internal bootstrapping, like I said, I'm sure you're probably familiar with the link prediction model, where you build some representation of the nodes and the edges, and then you use these to add new edges to your graph. But another way to use this is to find internal patterns. So link prediction is sort of more localized. So you just use the representation of the nodes and the edges, you compute a score, and you say, yes, there should be a new edge there. Internal patterns are things that are sort of a grander scale, and we are going to talk about that. So one other thing that I will do is you can use these internal patterns as they have been used before to detect whether you should add new edges, but you also can use them to help your pool model. So when you want to request a new information, let's say where is Cluj, right? So I say Cluj located in, and I search with Google for that. But maybe if I added a little bit more information, it would disambiguate my query. So if I say Cluj-Napoca, UBB, because I know that University Babeș-Bolyai is located in Cluj, then it creates a larger context, and it's quite likely that that will make my query more precise. So I will talk a little bit about that. So let's get to actual stuff. So the link prediction, like I just said, is an internal method. It just relies on this representation that you build. And like I said before, you can do it in two ways. Use just the representation of the nodes and the edges to compute a new score for an edge you think could be there. Sorry. Or you use some more elaborate patterns in various ways. And then the pool model of completion, where you use patterns together with the pool model. So these are the three things I'm going to talk about today. Simple link prediction, and see how we can compensate for imbalance when using that. Discovering internal patterns and using them for link prediction, and how we can actually use these patterns for this pool model, for targeted information extraction. Are you still with me? Yeah, good story? Kinda? Okay. So, like I said, this idea of embedding this symbolic system into a continuous space has started almost like 2011, I think is the first reference. And I think it's a fascinating process. It started with this idea that you can look at a graph and this adjacency information of a graph in a similar way as you look at word co-occurrences in a corpus. So for word co-occurrences, we had a singular value decomposition, do you remember? So we have these matrix factorization approaches that basically give you, in the end, vector representation of the words. So very smart people thought, well, why don't we do that for graphs? And in fact, there are a variety, so from the beginnings that sort of looked at the graph in relatively simple ways, so just as one big adjacency matrix or a collection of adjacency matrices for each relation type, things have expanded in very interesting ways, and there are these two references contain a very, very nice overview of all these endeavors. But I'm going to use one example from these ones because I think it's quite easy and intuitive to tell you what we did here to compensate for imbalance. So this approach here is called rescal, and basically it assumes that you can represent the graph through these. This is the graph representation. Is a 3D tensor. One of the dimensions is entity. The other dimension is also entity, so you have an entity by entity matrix, and the depth sort of are the relations in your knowledge graph, right? And the idea was that you can decompose this 3D tensor into a product of, so these are basically the vector representations of the entities, which are the same as these ones. This is the transpose, and for each representation is going to be represented as a matrix. As a square matrix, and every element in there will tell you the dimension x of the first entity, how strongly it interacts with dimension I of the second entity for this relation to hold between them, right? So the idea was that what you want is you want to approximate this 3D tensor, the Y, that's basically the adjacency matrix of your knowledge graph, through a product of this representation. And we add here some factors that basically try to prevent you from overfitting. So you want a compact representation of the entities with no many undue non-zero dimensions, and the same for the relations. So the way we compute each element of this matrix based on this decomposition is basically this scoring function. So the scoring function takes the transpose of the representation of the first argument, multiplies it by the matrix of the relation, multiplied by the vector of the second argument. And what you want is you want that number to be as close to 1 as possible if a relation exists, or I shouldn't say 0, but one of the interesting things about knowledge graphs is, can you think about something? So in terms of positive and negative instances, and so the graph basically is just connections. There's no sort of negative space there, right? So you don't know if an edge is not there. Is it not there because it's false, or is it not there because we don't know about it? So there is this complementary problem of selecting certain elements in this adjacency matrix and sort of postulating that they are 0, or at least they are not 1, so they have a lower value than the things you know. But anyway, so what you want is for these elements that you know the edge is there to be as close to 1 as possible, and for some that are corrupted, we call them, they have a value that's lower than 1. Because we don't know, it should be 0 or 1. So the idea is to try to build this approximation. So what happens, like I told you, sometimes when you have an entity that appears very few times, or a relation that appears very few times, their representation, so basically these vectors here, will not be informative enough. So the score we compute is going to be somehow misleading. So the solution for that is, at least for yeah, so this is sort of what I have said. These are some characteristics of the data set we are using. So one of the interesting things about these knowledge graphs, and in particular Freebase and NEL that I just mentioned we are using, is they have typed relations, right? So that means they have very particular constraints on their arguments. So when you have these relations like produced by, right? So one argument is going to be a movie, and the other one is going to be a producer, which is a person. So this sort of information from Freebase and NEL that these relations are strongly typed means you can put constraints on the arguments of the relations, right? So while we have very few instances, let's assume for this produced by relation, I could use the information that all the first arguments should be movies and the second argument should be a person, so that when I ask a question for a novel combination of nodes, then I can say, okay, well, but this one wasn't a movie, so it shouldn't, the relation should be false. So the way we did it is we introduced, we call this a regularization factor, which basically adds a new score that is computed between a node and its potential categories. So we also want those to be as close to 1 as possible, and those that are not true to be much lower. So adding this constraint sort of tells you, well, when we induce the representations for the nodes and the edges, it sort of skews the representation of those types of entities that abide by both the category and the relation constraints, and that will make us get more stronger representations, even for entities that don't have that much information. Or at least that was our hypothesis. So does this work or doesn't it work? So since our hypothesis was that even with little information, we should be able to derive informative representation. So we tested it by taking different percentages of the training data. So these are sort of overall results. So for 100% of the training, 75 and so on and so on. Bilinear is the original model, and ours is with the type regularizer, we call it. And these are the results in terms of mean reciprocal rank. So you see that for higher training data, our results are better, but for lower training data, we actually thought there is where we would help, the results are lower. So since it's not enough to look at this high level, because like I said, you can have arguments that are low frequency or relations that are low frequency, then we should have a deeper look. So here we looked at arguments based on their order of magnitude, right? So the first ones are arguments that appear less than 10 times, less than 100, between 10 and 100, 100 and 1,000, and so on and so forth. So there seems to be some middle ground where this approach helps. And we discovered that the reason is that where you have very few instances, the type representation sort of overwhelms all the other information that is out there. So this we confirmed with relation level. So these are relation frequencies. And finally, how are the colors? Oh, okay. So this is a sort of a 3D representation. Here is the origin, and this is basically this is argument 1 frequency, argument 2 frequency, and relation frequency. You see they are all very stratified. And what is very good and what we wanted is that at every level here, we would like to see an increase in the results, or shift towards red, right? That means higher value in terms of these mean hits at 10. So we accomplished that, and the same for MRR. And the conclusion of all this work was type helps. So we are going to set that conclusion aside, and we are going to integrate it in the rest in a second. So, like I said, positives, it generally helps. It does improve when it doesn't overwhelm, and this negative is that it hurts performance for low frequency relations. So that means that if we could complete our graph with other means, or at least add to it some more information, then our representation will be better, and adding entity types to that will also be better, will be even better. So let's see how we could improve or increase our graph. And the first one, I will talk to you about how we use patterns. How we use patterns for targeted information extraction. So, the first work that touched this topic was they noticed that if you have a source and a target and they are connected by one relation, oftentimes you find alternative, longer paths between the same two nodes. And they thought maybe that's a good thing. Maybe that's like an explanation for this direct link. And if we collect all those paths, we can use them as features in a machine learning process, and based on the paths that hold between these two, we can predict whether the direct relation exists, right? So for some entity, if we find it has the same nationality as some other person who lives in a certain location, maybe we can predict that it has, this person also has that as a place of birth. So from this idea, so this is what I just said. So the idea was, can I use this information, these paths that were before used only for link prediction, and do some targeted information extraction? So there was some previous work cited here, so it's West et al. And what they did is they used Google logs, Google search logs, to find associated entities. And the example they give was this: if you wanted to find out who Frank Zappa's mother was, and you type Frank Zappa mother, then you will get all sorts of irrelevant snippets back, because Frank Zappa's group was called the Mothers of Invention, right? So just this first matching is misleading, and it won't give you information. But if from these Google search logs you extract aggregated information, for example, the fact that he was born in Baltimore, then if you add these kind of pieces of information, your query is going to be more precise, and there is a better chance that the answer you search for is already there. So the question that me and Meng Fei, my master student, we asked was, can we use the patterns in the knowledge graphs, because we don't have access to the Google search logs? So are those just as good to find this kind of associated information? And sort of the question seemed reasonable, because the knowledge graph actually, that is what it tells you, things that are very relevant for a given entity. So we did just that. So first of all, we wanted to collect all these patterns. Yeah, okay, so I forgot this slide. So we wanted to take the data set based on Freebase and collect some relations, and for each entity that is represented here, find these kind of patterns in the knowledge graph and try to see if when we enhance a query with that and we send it to Google, we get better answers. So these are a little bit the dataset statistics. We use 46 relation types and several instances that we selected actually. So one thing about this path rank algorithm paths is that they are very numerous. So there are lots and lots of paths. So the average path per relation you see there sort of at least in the 50,000 range. So we had to do a selection, and basically what we did is it's an approximate precision and recall score. So we wanted to select the patterns that are very specific to our targeted relations, so the relations that we want, and also not patterns that just give you 1 or 2 hits, but that have a good recall in terms of the relations we want. So after we selected those things, here's a sample of the relation. We tried to keep approximately 50 patterns for each relation. If they were available, not all of them had those. We did this kind of experiment. So first of all, let's say our relation type is nationality here, and the path type that we selected from these ones available is that if this person that we are interested in was born in this particular place, and somebody else who is born here has this nationality, then this person has the same nationality, right? So one of the relation instances is this Andris Berzinj, who has the nationality Latvian, and this is the one of the instantiations of this path, right? So he was born in the same place as Carlis Viertes, who has nationality as Latvian, so then we induced that Andris Berzinj has the same nationality. So we designed, from this information, we made 4 types of queries. One of them that contains only the source and relation information, right? So it's just as we queried Google, like, what is the nationality of this person? And the next 3 options, we add gradually more information from this extended path that we have. So one of them was we add only the relations on this path, so just place of birth. The other option was that we add only the nodes, so we had this Carlis Viertes, and the last version is that it contains all the information on the path. So we wanted to see, when we send Google these query versions, do we get better results if we have more information like the one that these patterns provide? So basically that is exactly what we did. So we built these queries and we just send them to Google. I won't tell you how because it's not quite legal, right? So they closed the research interface, but we do a wget of sorts. So after we query Google, we take so it returns to you, just like you see on screen, 10 snippets. And we take these 10 snippets and our very simplified text, whether the answer is there, is whether this target entity that we are looking for is included in this test snippet. And that's a little bit of a shortcut, I know, but it's a complex information. So at least if it's there, there is a chance that the actual relation we are looking for is there. You may think about the fact that, yeah, there is also some language variation, right? So like you saw in the example, the nationality is represented as the country Latvia, but maybe it's Latvian, or so on and so forth. Well, luckily for us, Google search engine actually does some kind of processing. So by using Google, we sort of got a way of trying to deal with all these problems. So anyways, we computed precision recall and so forth on these things, and these are the results that we get. So the bottom here is the query in the original. So just the node and the relation that we sent to Google. And everything else, so this is a cumulative thing. The other one is the other 3 query extensions. So it was very encouraging for us to see that actually in about at least 60% of the cases, so more than 2/3 of the situations, by extending the query with this associated information from the knowledge graph, the query becomes more focused and the answer is not there. What we couldn't answer was which queries or which relation types are helped by this kind of approach. We didn't see any obvious trends in our data, so this bears more exploring and of course a little bit better evaluations at least. But also, so you saw these patterns, they look quite intuitive, but not all the PRA patterns are as informative. And so the next question becomes, how can we find some better patterns than what this PageRank algorithm gives us? So we are back to the question of looking at our knowledge graph, looking at the structure, and trying to find some interesting and useful patterns in there. So how can we do that? The knowledge graphs are extremely big beasts, right? So they are very, very big. And also, like we said before, they are incomplete and imbalanced. So immediately, any pattern that you're going to find is going to be affected. There is a bias there, right? So it's going to be, your search is going to be affected by these negative characteristics. So our hypothesis was that if we look at sort of a higher level of the graph, then maybe we can find some interesting patterns. And what higher level could that be? Well, that came for us from this work on the types that said, so when we looked at categories and we took them into account in our link prediction endeavors, the performance was better. So what if we had this graph that was at the type level instead of actual instances? Could that be helpful? So that is what we did. We built these so-called abstract graphs. So these are a combination of the types with the knowledge graph, where the idea was that we hope types will compensate for the lack of information. We'll have a much smaller graph to work with. We'll see how much smaller it is. And also, this idea of imbalance won't be felt because we won't care how many instances a relation has, because there will be one edge per relation, basically. And one of the interesting ideas was that we hope that these patterns that we find will be like high-level explanations for direct relations that can be used in different ways. And that already has the flavor of the discovering new knowledge that I was talking about, so moving towards that area. So here is how so a subset of the abstract graph would look like. So basically now we are going to take every relation type. For every relation type we are going to have only one edge. Its source and target are basically sets from the original nodes, right? So all the nodes that can appear as a source for this relation, all the nodes that appear as a target. So we don't have the actual information of which source is connected to which target. It's just like sets. And then on top of that, we are going to have relations like set relations that connect the new nodes that we built, right? So the, I don't know if you see colors there, but the black ones are relation types, like the actual ones. So this is institution, gender, profession, location, place of birth, and so on and so forth. And the blue ones here, these are set relations, like do they intersect, do they overlap? And they also have each of these edges can also have a numerical information attached to it. So for relation, for example, this would be sort of a relative frequency or a distribution in the data. So we can always use that if we need to. And the intersection ones will keep track of how big the intersection is, right? Because if it's very little, so for example, we have the relation between like capital city, right? So everything that's a capital city is a city, but a very small subset of cities functions as a capital city, right? So then you want, when you try to predict some longer path, you want to take into account these kind of links that are very, very weak. Okay, so what are we going to do? So we start with our knowledge graph, which we know has these imbalance problem. So this is a plot of for freebase. node frequencies versus, these are relation frequencies versus node frequencies. This is null, again, relation frequencies versus node frequencies. You see the imbalances is really, really high. So from this we build the abstract graph. We never lose the connection between the two, right? So whatever we are going to produce using the abstract graph, we can always project it back to the knowledge graph and look at specific instances. And from this one, what we want is to obtain these so-called abstract paths, right? So you can see here, so this is the stadium located in city. It connects to nodes, and this is an intersection relation. Stadium, home team, its target, intersection, and team plays in city. So basically, the abstract path is stadium X is a stadium located in city Y. If X has stadium home team Z, and Z is a team that plays in city, right? So it's a very nice explanatory link. So the big advantage, like I said, is that it's much, much smaller, and hopefully this will allow us to find better patterns. So here's how much it compacts things. So this is the, we did some experiments with freebase and NEL and their variations used by Gardner et al. So in this paper he describes how he built these PRA paths from this very, very large graph. So you see this one, freebase has 20 million nodes, and these are enhanced with some subject-verb-object triples from Reverb. And our graph has to the side of 4,000 nodes and about 22,000 edges, and the number of edges is high because of the intersection links. So for NEL, which is much smaller, the compaction is even more dramatic. So we were thinking that when you look at a graph in this abstract way at a higher level, the good patterns should sort of jump out a little easier. So the difference in how we build them, like I said, the PRA paths are collected through random walks for each particular source and target pair connected by relation R. They do these random walks and then find alternative paths that connect the two nodes. And then they assemble everything. They make the meta paths by discarding the nodes, so you only have the relations you follow. And then these meta paths are ranked by frequency. The abstract paths are much easier to find because we just do graph traversal, and since our graph is not even that big, this is not a big issue. So we can also compute the path weights based on the size of the nodes and the weights of the relations, like I said before. And here are some paths that we obtain. So this is a relation from freebase. It's called film rating. And on top you see the freebase PRA paths, and on the bottom the ones that we extract. So we were very excited because the paths we find seem very reasonable, so to speak. So if we were to imagine using this to find a new scientific hypothesis, it sort of feels that it has a good chance to succeed, or we should at least try it. So these are nice explanations as opposed to the PRA paths, which go a lot of back and forth between the type nodes, which we don't need anymore. So we did some experiments. Again, I show you the characteristics of the training and test sets because this is very, it will explain what happens with the results. So NEL is much more consistent, it has a reasonable number of instances to learn from for each relation. Freebase is a little bit less, so for some instances it only has 10 instances to learn from. And in fact, our approach works much better for NEL. So these are KGA are our results, and G is what Gardner et al. Report. So for NEL, our results are very good, and it's we find that very encouraging because, like I said before, NEL was explicitly built on this concept of coupled learning. So it actually relies on connections between different relations to learn instances better. Our way of looking at this abstract graph kind of captured exactly that. Whereas freebase is a little bit different. This phenomenon doesn't happen, but these results actually hide the fact that for many relations, our approach worked very well. But that was that. So we can draw some results from all this work that we did, that looking at a graph at this abstract level is useful. You can find very good and interesting patterns that hopefully will have applications beyond this just link prediction. And there are many ways to weigh and score this path that we extracted that we didn't experiment with all that much, so we just use a straightforward multiplication of the scores. And as a conclusion on these patterns, we found them very promising, so both for this internal task of link prediction, which we also tested it on, but we think that these patterns, particularly when they are so descriptive, can be used to actually complete the graph. Because if you have, so the way they have been used before was that if you have these paths between two nodes, then you postulate the direct link. But how about if you have the direct link, can you fill in some missing pieces when you follow this explanation, right? So that would be a very interesting thing to pursue. And then use that in conjunction with the targeted information extraction to complete the knowledge graph. So to conclude everything that I said today, I hope you will embrace knowledge graph because they have so many different facets you can exploit. You can look at them from so many different perspectives and incorporate them in your work, regardless if you work with symbolic methods or continuous methods. They are really useful also as visualizing methods. It gives you a different perspective on the data, which oftentimes is extremely useful. And that is all. Thank you.
Thank you. We have some time for questions, please. How do you model time? That would be the first question. And second, what do you have probability of connections between links, between nodes?
So, in general, I think how you model time could be dependent on your application. Psych, for example, have them as attributes on relation, because if you have Barack Obama president of the US, right, so he hasn't always been, sadly, he will not always be, but you can represent this information. We had that, so in the graph that I showed you from Regesta Imperi, we had the system that we use for visualization, whose name I forget because the students did that, but it had an additional timeline. So again, we associated an attribute with the edges, and then depending on how you fix the timeline, it shows you only things that have a specific value for the attribute in that interval. How do you work with that in a general problem? I think that depends a lot on what your problem is, and but I'm sure that there has to be a way.
And for link probability, can this be modeled as well?
So I think one of the ways we model the abstract graph is we use link probability, because it's not always, so for example, when you have the source of one relation intersected with the source of another relation or the target of another relation, right? So we assume that we can move from one like set of nodes to another one, but we move that with a certain probability that is actually the overlap. So I don't think it's problematic to model it. They are not usually modeled in the knowledge graph, but if you are interested in one of these embedding methods, right, nobody says that the adjacency matrix has to be ones or zeros. It can be any real value, and you're just going to approximate that. In fact, the score you're computing is going to be a real value. It's never going to be, rarely is going to be 1 or 0. So I don't think it's problematic.
Okay, one more question there.
There are the people.
No, we have time for 3 questions. It's fine. Please. Professor Vlad.
First of all, many interesting things and ideas, as you noted, interesting ideas, yes, for sure. And also, I just before, something in relation with the questions that about time, I wanted to ask you something. There are many definitions related to relation and to information relation. There are too many notions that need special explanation in an experiment. But just I ask, measuring the relation between, if you are looking for information about some relation. So I understood at the moment. You are looking, you said relation information. You just give an example, for example, nationality. And he was looking for information regarding that. But this information you are looking for are strongly dependent sometimes, other times less dependent, and sometimes independent. Therefore, I want you, and just at the moment you spoke about less dependency, not exactly in the same, using the same words as mine now, but I am sure that this was the sense. You have some, to say, for example, how do you measure in what time, I can say, the distance between this information you are looking for? There is a distance if you are looking, for example, in natural language. The distance you are looking for. You are looking for some things that are in some relation. And these things are not just nouns, but sometimes are notions. And you are looking for a distance between. That may be very interesting, but you have to put a limit at the moment in this type of searching. And if you are looking for dependence also, the dependence may be rise when there is a larger distance between what you are looking for. Just here, for example, can you explain me what about these images on your slide?
Yeah, so here we wanted to compute the results for link prediction. So like you said, we have a representation for the two nodes. We have a representation for relation types. And to decide whether this relation holds between two nodes, we apply our function. So in our case, it was this multiplication thing. And what we compute to test whether we did well or we didn't do well, this particular one is mean reciprocal rank. So basically, we look at the ranked list of our predictions based on the score we compute, and we score where our relation appears, right? So if our score is 0.5, let's say, and it should be a 1, so the relation actually exists. We looked in the ranked list of all our responses, and if this one is very high, so it gets 1 over the rank. So if this one is rank 2, then it's 1 over 2. This is the rank. Because what you want is you want to have rank 1. So that means you got the answer correctly, right? So this is just the scoring, and this is what the color shows. So it goes from 0 to 1, and we want to have most of them shifting towards. So if we improve the process, then everything would shift towards red. So that's all.
Strong relation in.
Did I say strong? So it's not about strong relation, it's about a relation score. So it's the strength of the prediction, not the strength of the relation.
But the rank means something was well predicted or what?
Yes. So if the instance exists, then if it's close to 1, it means our prediction is close to agreement. If it's something very low, then our prediction is not so good.
Okay, so
an answer related to the distance or time in a way we could come back to that.
I don't know if it's time, but definitely the function you choose to model how you combine the representation of the entities and of the relation, that's what matters a lot. So this one that I used is more complex than other ones. There are some that just look at the distance, right? So you imagine 2 points in the vector space, the relation is just the vector that connects the two. Or there are more complex ones that look at Gaussian distributions and so on and so forth. So that's
okay, so
what matters.
we're running out of time, sorry. Please have the other questions in the coffee break. We have 2 more papers until the coffee break. Let's thank again the speaker. Thank you.